Alright, happy March 8th, everybody. If you haven't been paying attention, there is an X-flare inbound, X5.4. This is life at 30. Actually, we should be going up to life at 40 in a second. That's me. I'm 40. And there it is, life at 40, alright. And here we go. So there's inbound X-flare. Communication issues. I'm going to try to get this loaded up. Hopefully people see some of it before things possibly shut down. This is not the end of anything. We all live, whether the meat does or not. We know the meat won't. This is the planet of death. Everything dies here. But you live, and you do live after it's over with the meat. So here we go. Asteroid talk.
Well, welcome back. Daniel Durder with us. Daniel, in terms of things going on in our own solar system, of course, Saturn's moon, Titan, full of methane. What other great mysteries are out there? What do you think's going on Europa?
Europa's a fascinating case. This is one of the four big moons of Jupiter. It's not a whole lot dissimilar in size to our own moon.
But Jupiter is so much bigger.
Really interesting because it has it's probably the one place in the solar system that has more liquid water on it than our own ocean, planet Earth. The story with Europa, though, is that ocean is hidden below this icy crust over the surface. So you look at Europa, we see this, it looks like Antarctica all over the surface, right? It's this big icy crust.
That's right.
That crust
is deep, right?
We know from the geophysical data, the gravitational perturbations from spacecraft as they've orbited in that system, that the interior, though, is melted. And we don't know exactly how far down below that ice. That estimate ranges anywhere from just almost near the surface in some spots to as much as 10 or 20 kilometers down. But someplace down there, we know there's a significant amount of water.
Immediately, I take my foot off the gas.
If you look at the moon just next door to Europa, called Io. Io is twisted and pulled by Jupiter's gravity to be one of not just one of, it actually is the most volcanically active object in the solar system. Right next door, though, Europa goes through similar tugging and pulling. It's that icy surface is cracked all over, and that tells us that down deep below that ocean, that rocky core below that ocean, I would be very surprised if there wasn't some sort of these hot geyser-like thermal vent sort of things like we see down in on our own ocean floors. You couple that energy source with liquid water. Folks are very, very interested in looking at Europa as a potential place for life in the solar system.
Could be. Now, but if there is life, life has to have something to eat, right? It's got to feed on something. What do you think's there for them to eat?
Well, here on Earth, that food source, that ultimate energy source, is dominantly, at least for most of the life that we interact with, it's dominantly the sun. And so plants evolve to take literally just the water vapor out of the air and the carbon dioxide out of the air. Use sunlight as an energy source to rearrange those molecules and make hydrocarbons, carbohydrates, sugars that the plants use for various things, and that we as parasites in the plants have ended up finding a pretty yummy food source on ultimately. So I use the sun as the energy source, but there are plenty of things we're learning now about the mechanisms in biology that are very creative and adaptive at using other energy sources. And we've now found that there are entire communities of life centered at these hydrothermal vents at the bottom of the ocean, deep, dark blackness that's darker than anything we've ever seen, using not sunlight, but the chemical energy of the sulfur-containing molecules in the materials coming out of those vents, and the heat of the vents itself as an energy source to manufacture the molecules that life then uses for energy. So you can have entire food chains that aren't necessarily based on sunlight.
All right, let's go to the phones as promised. We'll go to Bellingham, Washington to start. First-time caller, Nathan's with us. Nathan, go ahead, sir.
Hello, George. Hi, Daniel. It's my first time calling.
Welcome to the show.
Thank you. I'm a big fan of movies, and one of the movies that came to mind while listening to the program tonight was Armageddon.
Yes.
And so I kind of have a two-part question, I guess. In the beginning, it's like I was wondering if there was actually an asteroid that did wipe out the dinosaurs. And then, secondly,
65 million years ago.
if the type of scenario were to come up that happened in the movie, would we currently have the technology and the know-how to avoid an asteroid hitting Earth?
Oh, two great questions. Good stuff, Nathan. Thanks. So question one, did the evidence for an asteroid impact actually wiping out the dinosaurs? That was an extremely controversial proposal back in 1980 when that was first proposed. We've known for decades, centuries, that there was this mass extinction. Dinosaurs are no longer with us, obviously, thankfully in some ways. And so we've known about the mass extinction at the boundary between the Cretaceous period and the Tertiary period that we're living in today. This KT boundary is marked by those extinctions, but in 1980, a pair of scientists, Louis and Walter Alvarez, father and son team, were working in Italy, mapping some seafloor sediments that were laid down across that KT boundary, and they were interested in measuring the rate at which those sediments were put down. They weren't worried about impacts or things like that, but they were just looking at how fast those sediments were put down, and they were using the infall, the slow, steady infall of cosmic dust on the Earth all the time, and the iridium, platinum, rare earth platinum group metal, very, relatively abundant in interplanetary dust, as a sort of a marker of the rate at which that dust was being put down and those sediments were being laid down. But they found that right at the boundary itself, there was a huge spike in iridium. I mean, just, thousands of times more abundant than the background. And that piqued their interest, and when they sort of calculated, well, gosh, how much cosmic material coming in all at one time would you need to make a spike that big? And when they ran the numbers, it turned out that it added up to something like an asteroid, 10 kilometers across, 6 miles across. And it kind of hit them as like, holy cow, this might be the actual source of that extinction itself. It might have been an actual cosmic collision. Back at that time, it was, that was the idea, but there was no evidence for an actual impact at the boundary at that point in time, 65 million years ago. Around 1990, though, the Smoking Gun Crater itself was actually discovered in the Yucatan Peninsula of Mexico, and so over the intervening years, as people have researched that crater and the details, that's one of these transformative, paradigm-shifting events in science where all the evidence comes together in a way that you just have these aha moments, and it's now pretty much one of those. It's about as firmly established as anything could possibly be in science. Big impacts are bad things for sure. Now, if something like that were, on the Armageddon movie scenario, or the other movie that came out about the same time, Deep Impact, two movies made with this realization that we're living in this cosmic shooting gallery, and is there anything that we can do about it?
We are.
There's a kind of a flippant statement that while the dinosaurs went extinct because they didn't have a space program, but we do, and we could actually use that technology to our advantage, and this is the one natural disaster that we actually could prevent. Now, an impact of that scale right now today, probably not. We're not. I have to tell you, really, quite frankly, we were just not prepared for something of that scale to be able to actually physically do anything about it. Unfortunately, it's a sad truth, but it is true. The good news is that the surveys, the telescopic surveys that are responsible for finding all these things, have kind of put us in the clear. This used to be something we worried about back around 1980, 1990, but the subsequent searches have showed us that for objects of that scale, over the lifetime of you and your children and our grandchildren, that's not something we have to worry about, thankfully. So that's money well spent.
What about wormholes? Can we get sucked into one? Can the entire solar system, galaxy get sucked in by a wormhole?
I guess if there was some stellar mass black hole wandering through our stellar neighborhood, and we're to pass deep enough and close enough through our solar system, it would certainly cause, you've got all the gravity of that stellar perturber, in one point source moving through the solar system. It would cause a significant perturbation to the orbits of the planets in our solar system, that's for sure. But one thing I think we want to kind of dispel the myth of black holes and these sort of things acting like big cosmic vacuum cleaners out there in space. it's the same gravity that the sun has, right, or any other object, and it's all focused in one point source rather than a distended source like the sun. But the effect of a stellar mass black hole passing through our solar system would be no different over the broad scale of the solar system than a star passing through the solar system. So wouldn't be a happy event for sure, but I don't think we'd be disappearing in a flash of light, that's for sure. Not for an event like that.
West of the Rockies, Victor is truck driving in California and on the air. Hi, Victor, go ahead.
The air, next 6 miles.
I've got a question.
Sure.
Protocol. If you find something, just a scout, what's the protocol of who you tell and what do you do about it?
All right, what's our procedure if you find an astounding thing, Daniel? How do we do it?
Excuse me, cough. I'm getting over cold.
All right.
Yes, there are protocols, and I'm assuming if you're discovering something like an asteroid, we had this situation I described earlier where one of the folks we funded from the Shoemaker grant actually discovered the asteroid that has been in the news last week. In the case of discovering an asteroid, if you're an amateur astronomer and your CCD camera happens to capture one of these objects, the place to go is the Minor Planet Center in Massachusetts. There's a Google up the Minor Planet Center on the web, and they have a procedure for reporting the sky plane equivalent of latitude and longitude that we use for locating positions here on the Earth. There's an equivalent system up there in the sky called right ascension and declination that we use for reporting the positions of objects in the sky. And those are the kinds of coordinates that you would report to the Minor Planet Center. And the object is given, once an orbit is connected through the positions for that object, it's given a provisional designation. And then in the case of an asteroid, if you're the discoverer of an asteroid, you then earn the right you maintain and earn the right to get to name that asteroid, which can be a lot of fun. Not that I've discovered any myself, but I've actually been responsible for naming several asteroids after some NASA test pilots I flew with, and the producer-director of the Babylon 5 TV series and things like that. It's been a lot of fun. So getting to name one after yourself is pretty cool. Sure. It's even better if you discover a comet. Unlike discovering a asteroid where you get to name it, if you get to discover a comet, it's even better.
It's your name.
Usually, they end up naming the comet after you.
That's right.
So you want to go out and discover comets. That's the fun.
Shoemaker, Levy, things like that, right?
Absolutely.
Let's go to Oswego, New York. Tim's with us on Coast to Coast. Go ahead, Tim.
Yeah, back in the late 70s, late 60s, early 70s, there was a green ball of fire that came across the sky. It lit up, it was just after dark, and it lit up like daylight. Everything was green.
Sounds like a meteor.
Ever recorded?
What you saw was most certainly a bolide, a pretty. I want to say a common event. It's not common to be that bright. I mean, it's kind of a rare and fun thing to get to witness. So you're very lucky that you got to see something like that. I've been watching this guy for all my life, and I've only seen one or two reasonably bright sort of things.
Yeah, they go by so fast.
Yeah, they go by so fast. You gotta be just really lucky to see something like that. So what you saw was most likely, if it was really bright enough to really flash and light up the sky, you're looking at something, maybe marble size or walnut size passing through into the atmosphere. A piece of rock. I mean, you witness the end of a piece of stuff that made the planets in the solar system that have been wandering out there for 4.5 billion years, and you got to see it on the day of its death in the Earth's atmosphere.
How could an object the size of a little marble or a grain of sand cause so much light when you look at it?
Oh, it's a phenomenal amount of energy that's dissipated in the atmosphere when an object that comes streaking in at 20 or 30 kilometers a second. The energy of motion of an object is dependent on the mass, the size, but the mass of the object. So that's important, but not nearly as important as the speed. If you double the mass of something, the energy that it's going to deliver when it stops goes up by a factor of 2. If you double the speed of the object, the amount of energy that gets delivered goes up by a factor of 4. It goes up as the square of the speed. So as you ramp that speed up, the energy gets deposited, goes up really fast. And so most asteroidal material entering the atmosphere is coming in at 20 or 20-ish kilometers per second. That's, think about how much energy the space shuttle